Hey Calculus class! Tonight we're going to talk about topic 44, volumes of solids of revolution, by using what's called the disk method. So what we already know about volume: if the cross section is perpendicular to the x-axis, then we're going to integrate from a to b of the area of the base times dx, so in terms of x. And of course, this is the area of the base of your cross section. If the cross section is perpendicular to the y-axis, then that means that we are going to integrate in terms of y, where a of y is the area of the base of your cross section, but in terms of y. Now, what if we rotated a function around an axis? What would the cross section look like then? So visually, if I was to take this function right here and rotate it around the x-axis, I would create this kind of bowl-shaped figure, so that when I sliced it, my cross-section is this very thin cylinder. So we call that type of cross-section a disk, or a very thin cylinder. Now, how would you calculate the volume for this solid? Well, the 2D cross-section is a circle, so that means you would want to integrate the area of the circle, which means we find the radius of the disk in terms of x or y, and we use the fact that the area of a circle is pi times the radius squared. And if you look in your picture of the circle, which is the top part of this cylinder, right, from the top to the bottom curve, that represents your diameter of the circle. So therefore, your radius is half of that. So in this case, happens to be the top curve to the axes. And of course, this is what we'll be integrating. So let's look at an example. We're going to calculate the volume of the solid formed when f of x equals the square root of x is rotated around the x-axis from x equals 0 to x equals 1. So if we're going to take a 3D view, okay, the square root function is this top function right here. That's what's getting rotated, and it's going from x equals 0 to x equals 1. 2D, if I was just to look at where the radius would be, the radius would be the top curve to the axes, which in this case would be my vertical rectangle. So to get the value of the radius, because we have to do pi r squared, the radius is going to be your top curve minus your bottom curve in this case. So since our radius is our top minus bottom, you'll see that the top curve is the square root function, and in this case your bottom curve is the x-axis, which is represented by y equals 0. So that means my radius, which I'm going to call r of x, is going to be the square root of x minus 0, which of course is just the square root of x. And that's what I'm going to integrate. I'm going to integrate pi r squared. And since pi is just a multiple constant, I can pull it out of the integral sign. So I'm going to integrate pi from 0 to 1 of the square root of x squared. Simplify that a little bit. Makes it really nice and pretty. Integrate, and then evaluate. So the volume of this solid is pi over 2. All right. Let's see if you can, let's look at this example. So with this example, we're going to calculate the volume of a solid formed when f of x equals x cubed is rotated around the y-axis from y equals 8 to y equals 0. Y equals 0 to y equals 8. So visually, here we have x cubed, and it's only the x cubed part from 0 to 8. So this is the part right here that I'm rotating. And when I rotate it about the y-axis, that means I'm going to get this thin, elongated bowl shape. So if I was to look at it 2D, here's the x cubed from 0 to 8. And notice this time my cross section is horizontal. So that means I'm going to have a horizontal rectangle. So that means I'm going to have to integrate in terms of y. Okay. So in this case, the radius is going to be the right curve minus the left curve, which the right curve in terms of y is y to the 1/3, or cube root of y, same thing. And your left curve is the y-axis, which is x minus 0. So that means my radius this time is going to be in terms of y, right minus left. So my radius is y to the 1/3. Set up my volume integral. So I'm integrating pi r squared. And I'm going from 0 to 8. They gave me the y limits. Go ahead and simplify. Add 1 to the exponent, divide by the new exponent, and then evaluate from 8 and 0. So I get 96 pi over 5. All right, so volume by disks. The first thing you have to keep in mind is that if the solid consists of an adjacent vertical disks between x equals a and x equals b, we find the radius r of x of the disk at x, and the volume is given by pi times the integral from a to b of r of x squared dx. So this is just telling you that you're integrating in terms of y. So you have vertical disks, aka vertical rectangles. And of course, r of x is top minus bottom. And here's a visual, if you would like to look at it. You have your horizontal axes of revolution. It's not necessarily always going to be the x-axis. And there you have your vertical disk. And of course, the change of x is the same thing as the d of x. And then the second one is if the solid consists of adjacent horizontal disks between y equals c and y equals d, we find the radius r of y of the disk at y, and the volume is represented by basically the same thing, but in terms of y. And this time your radius is represented as right minus left. So visually, this is basically the same picture. It's just this time your disks are horizontal. And your axis of revolution is vertical. All right, so let's see if you can try these next few problems on your own. All right, let's see how we did. For number 1, you calculate the volume of the solid bounded by y equals square root x minus 1, x equals 2, x equals 5, and y equals 0. And it's rotated about the x-axis. So I'm going to graph the functions I'm given. Okay. And I am rotating this function around the x-axis. I'm bounded by x equals 2 and x equals 5, so those are my limits. Since I'm going around the x-axis, I'm going to have a vertical disk, so that means I'm going to integrate in terms of x. So to get my radius, I'm going to have to do top minus bottom. So in this case, my top function is square root x minus 1. My bottom function is the x-axis, which is just minus 0. So I'm going to go ahead and set up my integral, simplify it a little bit, integrate, and evaluate to get 15 pi over 2. All right, let's see how we did on the second one. Calculate the volume of the solid bounded by x equals y minus y squared and x equals 0. And this time it's rotated around the y-axis. So we aren't given any limits, so we need to find the intersection points. So I'm going to set the two functions equal to each other, x equals 0 and x equals y minus y squared. So I'm going to set them equal. Just a quadratic, so I'm going to solve for y by factoring. So we get y equals 0 and y equals 1. Now I need my right and my left curve, which in this case my right curve is the y minus y squared, and my left curve is going to be the y-axis. And the one way you can do this if you couldn't graph this is pick a value between 0 and 1, plug that in for y, and you would get that this value is larger than x equals 0. All right, so I'm going to go ahead and integrate the radius squared. I'm going to have to expand that out. Go ahead and integrate, evaluate, and simplify. So you get pi over 30. Well, I hope you enjoyed learning volumes of revolution by the disk method, and I will see you in class tomorrow. Have a good night.